Good evening, dear colleagues, dear friends, dear members of the ProISSI Association. As usual, it's my very great pleasure to welcome you to our tonight's evening talk given by Dr. Karel Schrijver, Johannes Geis Fellow of 2018, and it's my very great pleasure to briefly introduce it to you. So Karel Schrijver received his PhD at the University of Utrecht in the Netherlands on the topic of solar and stellar magnetic activity. After postdoctoral appointments at the University of Colorado and the European Space Agency and fellowship of the Royal Netherlands Academy of Sciences, he joined the Lockheed Martin Advanced Technology Center, where he eventually became a senior fellow, which is equivalent to director. His research focuses on the magnetic field activity of the Sun, the coupling of the Sun's magnetic field into the heliosphere and its solar wind, the manifestations of magnetic activity of other Sun-like stars, and the impact of solar variability on planet Earth and its inhabitants. He has published over 260 papers, 155 in referred scientific journals, co-wrote the first textbook on solar and stellar magnetic activity, and was lead editor of the 5-volume Heliophysics series for beginning graduate students, and published 2 popular science books, one entitled Living with the Stars, on the multitude of connections between the human body, the Earth, the planets and the stars, and the other one entitled 1 of 10 billion Earths, which was recently released in fall 2018 about exoplanetary systems and what they tell us about the Earth as part of the solar system. So based on these huge achievements, he was then awarded the Johannes Geis Fellowship 2018 and is now here at ISSI during his first stay, as I just learned, and the second stay will then follow in fall this year. So it's my very great pleasure to welcome him tonight, and we are looking forward to his presentation on solar magnetic activity. Please, Karel, the floor is yours.
Thank you very much for the nice introduction. Good evening, everyone. Thank you for coming out in this wonderful weather. First of all, let me thank you for coming, but also thank ISSI for awarding me this fellowship, which I consider a great honor. And it's a real pleasure to be here. I just computed this is my 16th visit to Bern, so I'm not a newcomer to this institute. And I've always loved coming here because it offers the opportunity to focus on science with little interruption in a wonderful setting. So I'm glad to be back. My talk today is about solar magnetic activity, a topic that I've worked on for at least 3 decades, and which is still continuing forward quite rapidly. And obviously, because of all those advances, I'm going to have to tell you about that in a nutshell. So briefly, I don't mind interruptions. If you have a question, if I say something incomprehensible, please feel free to raise your hand. I'll be happy to answer questions. What I'll try and do is go through some of the major challenges that we're still facing in understanding the activity of our Sun, and also place that in the context of what we're learning from and why we need to learn from other stars, and in fact, why even the presence of exoplanets, as we now know, is not only of interest to understand because we'd like to know about exoplanets, but exoplanets may actually help us understand what solar magnetic activity is about. But I'll get to that at the very end. So let me first begin with introducing to you the Sun. The Sun is, if we look at the top left-hand diagram, it's a Hertzsprung-Russell diagram, which is basically the brightness of the stars versus their color. Stars in general spend most of their adult lives, when they have sufficient fuel in the form of hydrogen and eventually helium and later stages, on what we call the main sequence. That's that diagonal line on which they stay. And once they begin to run out of energy, they migrate off that main sequence and either become giants or eventually, if they don't explode in supernovae, become white dwarfs. But I'm going to focus on primarily the stars on the main sequence, like the Sun. What all these stars have in common that are on the right-hand side is that they all have some signature of magnetism like that occurs on the Sun. So by looking at all of these stars, we can also from that infer what the common processes are that should drive what we call the dynamo process in a star, like the Sun. That's summarized on the right-hand side in the top diagram there. All of the stars that are essentially yellow, orange, or red, the cool ones, and that's why they're called cool stars, have immediately underneath their surface a convective envelope where energy is being transported by overturning motions of an ionized gas. By looking at all these stars, we can also infer that what sets the strength of the dynamo is the rate of rotation of the star. We can look at young stars and old stars and stars of different binary systems where the rotation rates may be influenced by the presence of the binary companion, from which we can infer, no, it's not the age of the star, it's really the rotation rate of the star in combination with the convection immediately underneath their surface that drives what we call the dynamo and sets the strength of the dynamo. And the sun, in a sense, is common in that all of those stars are doing things like the sun. The sun is uncommon in one way, and that's the intent of the diagram in the lower right there. It's on the warm end of the cool stars. And the cooler you go, the more stars of a given spectral type actually exist. So there are many more orange and red stars in the galaxy than there are the yellow ones. If you go towards a star that has an even shallower convective envelope, with the ones we call the A and F type stars, activity begins to fade. So we're in this interesting environment where we have a star with a sufficiently deep convective envelope to maintain a nice high level of activity. It's not one of the most common stars that are also fainter. By the time you go to the more red stars, they become fainter, so harder to study. So the yellow ones are nice and fairly bright, but not so bright that they wouldn't have magnetic activity anymore. The one advantage that the sun has, apart from keeping us warm at night, is that it is nice and close, which means we can study it in great detail. I'm going to take you some of those details. One of the details has to do with the way that we can actually study the interior structure of the star. We use helioseismology. We use sound waves running through the interior of the star to establish the general structure, but also a good deal about the dynamics of the internal part of the star. And if we look at that, in this diagram, we're looking at the largest scale flow patterns, the largest scale dynamics. We see that the core, the internal structure inside that wide ring, is rotating like a rigid body, although there's nothing solid about the sun, it's all gas, but it's rotating pretty much like a solid body. We're not quite sure about really the depth near the center itself, because that's hard to probe helioseismically. But the bulk of that volume is rotating as a solid. That disappears when we look above that white line. Above that white line is where the convective motions occur. And the convective motions have a way of transporting angular momentum, setting up stresses in the system that eventually lead to the equator rotating substantially faster than the poles. And contrary to, say, what happens in the interior of the Earth, or contrary even to initial expectations, we're not looking at rotation on cylinders away from the rotation axis, but wedges. So you basically look at a series of nested cones that show you that whatever we see at the surface apparently persists at the same rate going down towards the center of the star. On top of that is a second pattern of flows, harder to detect, it's slower, but equally important for the dynamo action, and that's there is a meridional advection. There's a large-scale flow from the equator of the star to the pole at the surface. At depth, there has to be a return flow. Most models of the dynamo are still assuming that there's only a single one of these cells going on. So at the surface, you go towards the poles, at depth, you go down, and that transports the magnetic fields around. Helioseismic observations are beginning to suggest that actually there may be at least two of those nested structures on top of each other. But this is a very difficult measurement to make. The flow is of order 10 meters a second at the surface. Now that sounds reasonably fast. You'd have a hard time walking that rate. But given that the convective flows on the smallest scales, the overturning convection in the granulation patterns is of the order of 1 kilometer or thereabouts. The thermal line widths are of the order of 6 kilometers. It's really hard to pick out something that goes at a few meters a second, particularly at depth where the density is higher and therefore the flow correspondingly slower to maintain the same overturn motions. So we're not sure what happens at depth. We do know what happens at the surface. The surface is the one place we can easily see. And at the surface, we can see these things like sunspots. This tiny sunspot could hold the Earth in its center easily. So this is an astronomer's term of tiny. These are substantial structures. The field that's generated by the dynamo, I'll show you that in more detail in just a moment, penetrates the solar surface and extends into the atmosphere. In the atmosphere, it carries waves, it carries electrical currents that are dissipated and heat the outer layers. The outer layers are hotter than the surface. So whereas at the surface, we're looking at about 5,000 Kelvin, I'm rounding off numbers, it can reach up to 5 million in some regions in the atmosphere, so considerably hotter. In between the surface and that hottest domain lies what we call the chromosphere, a region that is partially optically thin, partially optically thick, partially dominated by magnetic fields, partially dominated by plasma flows, partially ionized. It's the most complicated region to understand, and I'm not going to touch it any further. I'm going to jump to what sits above that, the corona, which is also a hard one. But the corona is largely optically thin. Light goes right through it. But in order to see that light, you have to go to a place in the universe where you can actually receive the light that's emitted by the corona. The bulk of the emission is visible, is invisible to the human eye. It's extreme ultraviolet and X-ray because the temperature by now is 1 million degrees to about 3 million degrees in quiescence, 10 million degrees during explosive phenomena. So we have to go to space. And that's why I joined Lockheed Martin, because they were building this wonderful instrument that was initially the TRACE satellite and later the Solar Dynamics Observatory, where we have, and it's with the latter one that we've made these observations of the solar corona. You'll see that the sun itself in this image is a black sphere. The surface doesn't emit at these wavelengths. We're just looking at the glow of the atmosphere proper. You'll also see that there are also these line-like structures there. That's the magnetic field is basically holding on to the plasma that's ionized and guiding its motion. So it's not a uniform atmosphere. It's heated where the magnetic field is strongest, and it's held by the magnetic field and guided along it as it flows up and down. I could show you a whole series more of these different colors, all artificial colors, because we don't see it with the human eye, but I'm going to keep it at this. And I'm going to add the one thing that we really ought to want to understand, namely, how does the magnetic field lead to this heated atmosphere? Well, we can measure the magnetic field that sits underneath that atmosphere by using essentially Polaroid glasses, polarization, light that goes through a magnetized, ionized atmosphere, leaves a polarization signature, so we can measure the magnetic field. But we can only measure the magnetic field where that light comes from, so at the surface. We would like to know the magnetic field in the atmosphere. Now, one way we can do that is by using a model field. Assuming the field is largely potential, we can extrapolate it from the surface and we can make line drawings like this. And in fact, if you look at the comparison of these line drawings with the observed emission structures, it works reasonably well. Except where it gets interesting, because where it gets interesting, there are currents running through the atmosphere, and these currents are not captured by this kind of extrapolation. I'm going to come back to the complexity of that in a moment. Now, you may have noticed that I'm showing you pictures of 2010. That's when I was heavily involved in working, well, and after, in working with the Solar Dynamics Observatory, which was just launched by then. But that's not the reason for choosing that date. The sun goes through an 11-year cycle. And this is a diagram of the last few of these cycles, where the number of sunspots rises and falls at roughly every 11 years. Currently, we sit in that trough, a cycle minimum. So there's really not very much going on. So I'd like to show you the prettier pictures of an active sun. So I'm going back a few years, which puts it actually at the top of that most recent solar cycle. If you look at the solar images today, you'll see a small sunspot, 2 small sunspots. I was preparing this set of slides last week. That was what the sun looked like a week ago. There was absolutely nothing on the disk. Well, if you look at it in detail, you see all sorts of things, but there was no activity of substance on the disk at all. The observations of sunspots, of flares, and all the other solar activity extend by now for almost 400 years, and this is a collage of a few of these observations. When Galileo Galilei started pointing his telescope at the sun and other things, one of the things he noticed and started drawing on the top right-hand side there is how sunspots were moving across the solar disk, from which he inferred it was a rotating sphere, that they changed in time. They were not fixed structures. And by the way, also establishing that the sun was not the immaculate sphere that everyone assumed it to be at the time. So we have 400 years of direct sunspot records. I'll show you a little bit of that record in just a moment. Knowledge of the fact that the sun also had explosions didn't start until about 160 years ago, when Richard Carrington and Richard Hodgson, you can read about this, in 1859 observed the first thing that now is known as a flare. Then it was known as a singular appearance because they didn't know what it was. It had never seen before. From those flares come eruptions from the sun, known as coronal mass ejections, that carry not only the plasma, but also magnetic field. And when that envelops the Earth, it can interact with the Earth's magnetic field to create geomagnetic activity. And I'll go back to that slide so you can see it again. The movie isn't playing. You can see one of the footprints of geomagnetic activity in the aurora, which are here observed from the International Space Station flying over the southern hemisphere, somewhere around Madagascar, I think, at the time. We didn't know what medium carried the explosion on the sun to what happened in geospace until we learned first about the solar wind, which was in the late 1950s, early 1960s. We didn't know about the strong variability, these things called coronal mass ejections, until about 1973, I think, when the precursor of the space station, the Skylab space station, had instruments on board that for the first time actually saw a coronal mass ejection leaving the sun, and people started connecting the dots, literally. Before then, people may have seen a coronal mass ejection during an eclipse, but an eclipse is so short-lived that you don't actually see anything evolve and change during an eclipse. So even if there had been a coronal mass ejection, you just wouldn't have seen it move. It took space-based observations before we could connect those dots and understand that the coronal mass ejection was the driver of much of the intense forms of space weather. Now, this dynamo, it keeps eluding us. We can make nice sketches, highly simplified concepts, but I would say we don't actually have a dynamo model as yet. We don't know why the sun is as active as it is. We don't know why it has an 11-year cycle. We don't know how it generates flux tubes and active regions at the surface. We don't know why it makes sunspots at all. But we're getting closer. People have gotten a long way beyond this kind of diagram, and you can look at simulations of what magnetic fields are doing inside the convective envelope that are getting a great deal of fidelity, like this one with spaghetti noodles floating around, but this is supposed to be the magnetic field traced in the convective envelope. The difficulty lies in the fact that the sun is a big body. It's 1.4 million kilometers across, and the relevant scales are small compared to that. So computers can't deal with everything. You have to simplify at some point. And typically, like in models like this, they leave out the top, say, 50,000 kilometers of the 1.5 million. Now, that doesn't sound like much, but the atmosphere is so stratified that half of the pressure scale heights sit compressed in that outer layer. So you're basically missing all of the details of how field comes through that layer to the surface and creates the phenomena that you're seeing. Plus, that very emergence is an essential ingredient of the dynamo because that field is the seed field for the next cycle. So we're still a long way from running a full cycle in a computer. It also means that forecasting dynamos, the ultimate test of do we understand them, is still very difficult. This is a number of sunspots over time over that most recently completed cycle. And there have been a large number of predictions. This is actually in a series of categories, the total number. So there were 54 predictions of how strong that cycle would be. And interestingly, the average is right on. The question is it right on for the right reason? And we're still puzzling about that, because this cycle, being of average strength, you wouldn't be too surprised that an average forecast gave you an average strength cycle. I remain somewhat skeptical about this. We'll see. All we have to do is wait for another 10, 20, 30 cycles, so a few centuries. That's not good. This, again, is why I think we really have to connect with our stellar communities, because there are many stars cycling like the sun does. And if we could combine that, we would do essentially what, say, a medical doctor would do, not study a single patient, but study a patient population to learn things. This is a record of the last 3 centuries of that sunspot number. And that little diagram inset that's showing up there is a combination of here, one, the last cycle of which I just showed you the forecast, and the latest, newer forecast of the next cycle. Again, average. We'll see if that materializes. 5, 6 years from now, maybe I should give this talk again and see what happens, because then we'll know where we are. There are many other details that I'm not going to get into. They're fine structures, very weak patterns that are nonetheless brought out, like slight torsional oscillations, things that are going slightly faster and slightly slower than the average. And you can make diagrams in which, as a function of time, you measure the directions of these flows. The main thing I'd like you to see over there is the scale of this. This is expressed in nanohertz. 10 to the minus 9 of a signal picked out of a 5-minute oscillation, which is 10 to the minus 3. So they're a factor of million below the frequency of what you're looking at to pick up the frequency of the flows that you're looking at here, which means that the only way you can do this is have very stable instruments that look at the sun for a very long time without interruption. That's another reason to go to space. Our seismologists are also beginning to learn to pick up the signal of emerging flux about to form sunspots, even before it comes to the surface. This is a little combination of observations at depth, 60,000 kilometers below the surface, and the formation of that region at the surface. So we see the signal, the perturbation, although processing it takes almost as long as the region takes to come to the surface. So it's not really a forecast, it's picking up where it's going to be. But we cannot tell from that kind of observation what the magnetic structure will be. So we don't know about the potential of eruptions. We can just say there's something big coming to the surface, and it may or may not erupt. All of those fields at the surface form the foundation of the entire structure in the field flowing out in the solar wind through the heliosphere. If you'd like to know what's heading towards any particular planet or spacecraft, you'd have to configure all of those together. And now we have to realize, well, actually, we're only seeing a part of the full sphere. And the sphere keeps rotating. And the regions keep evolving. A typical active region lives for a few days, the largest one for like 2 weeks. There's a month-long rotation of the sun. And we can measure the fields only where they're not near the edge of the sun. So we have access to about 1/3 of the total surface. 1/4, if you're very picky about, and 2/3 or 3/4 to do clever things. Here's an interesting experiment where people are saying, well, we can try and use artificial intelligence here. There was a time when at least we had a back view of the sun because we were looking at it with the stereo spacecraft that looked at coronal images. It wasn't measuring magnetic fields, unfortunately, because it wasn't carrying a magnetograph. And these people have tried to put together an artificial intelligence that says, guessing from the images in the EUV, this should be the configuration of the magnetic field. And they're doing not too poorly. I won't go into the details. So there are interesting developments going on where machine learning is now being applied to understanding space weather. What is really hard, however, is to do it in the details that are, as I keep coming back to this, that are of interest, the ones that explode, the ones that drive variability. And the reason is this: the sun is rotating, the magnetic field is always changing, it's changing on all sorts of scales, and we're seeing it only a fraction of the time. Now, it gets a little bit easier if I remap it like this. So now you're looking at a map of the sun unwrapped around the sphere. And that black oval moving around is basically where the front of the sun is at any one time. And we can let our computer models move magnetic field around at other times. So you can see it's actually all dynamic, even when the front of the sun is not overlapping with it. But you'll also see that as the front sweeps over that model, it keeps updating it. There are either new regions or the flows were not what we thought they were. So although we're getting better at this, we're not capturing it because it needs to be observed. You'll see there's a lot of fine structure here. And I don't know if you're thinking about this, but when we think about the Earth's magnetic field, we typically think it's a dipolar field. It has some quadrupolar and higher order perturbations on it, but it's dominated by north on one side, south polarity on the other side. The sun looks to be different. It isn't quite as different as that, because if we take the Earth away and look at the Dynamo model that was run to create this field, you'll see there's a lot of structure on the inside. The difference with the sun is at the sun, we're looking at the top end of the dynamo itself. The Earth's dynamo sits much deeper. So if we step away on the sun to a similar distance than we are on the Earth, there too, it's dominated by the dipolar and quadrupolar field, which is what becomes the heliosphere. So they're not as different as they seem to be in structure. They're definitely different in dynamics, because everything inside the Earth is far slower than the overturning motions are on the sun, because there's a difference between heavy metals moving around and light hydrogen moving around. Sometimes we can see active regions emerge. And here what you're seeing is a bundle of flux that was somehow generated in the interior of the star coming to the surface. And because it's coming through that convective layer, it's being frayed into strands that eventually, after the emergence, it'll cycle again, sort themselves out into one polarity on one side and another polarity on the other, probably because there is some structure at depth. But the layers near the surface that I mentioned earlier, all these pressure scale heights packed into that small distance, and cause the field to rapidly expand, fray, and then it has to sort itself out. But in doing that, it also picks up through the flows entanglement of magnetic fields. Movements of magnetic field essentially is energy in it. You could call it electrical currents. The release of that energy is what forms space weather. Now, computers can do a remarkably good job at this kind of thing. Here's a simulation where they say, we'll take these two concentrations at the bottom and let flux emerge. And then at the surface, as it begins to come through the surface, you can see that the magnetic field distorts the convective pattern. Eventually, these structures begin to sort themselves into one polarity here and another polarity there, and you can see sunspots form. In this case, smallish ones. We call them pores, not full-fledged sunspots, because for that, the domain of this computational experiment was still too small. But it is very promising that so many of these features that we see in real life can be mimicked in the computer, not on a one-to-one match, because that is something we cannot do, but in patterns, we're doing remarkably well, except for the fact that we have to hold the field down here, because otherwise it too would drift away. So something in the sun manages that for us that we just don't know yet too much about. Now I'm going to move from this layer, the surface, into the atmosphere. And I'm going to show you a movie and introduce it with an image. This is a still image of a small section of the solar surface. I'll show you just how small it is by putting a little image on top of it. That is a map of Switzerland to scale. So when I say a small sunspot, I mean something really big. You can also understand that there are things happening below the scale of Switzerland, like you are smaller than the scale of Switzerland. The smallest scales we'd have to look at on the sun would be of the order of a few kilometers. The smallest scales we have access to are several hundred kilometers at the very best, and only at the very best times of observations. This particular observation and the series I'm going to show you are sort of a 1 in a million shot. The Earth's atmosphere was particularly quiet. The observers in the telescope were really good, and it took a mere 3 million computer node hours to actually sharpen up the images and stabilize them to what I'm going to show you next. I'm going to show you this dynamic. Now, this is the layer above it. So we basically tuned the wavelength to a layer of the atmosphere, to a wavelength for which that layer of the atmosphere is opaque. You're seeing strands and striations. You're basically literally seeing the gas tied to the magnetic field. And you will see how it's moving up and down along it. You also see that it seems to be cut off like grass at the top. The field doesn't stop. The gas doesn't stop. That's where the corona is. At that point where you see it cut off, apparently cut off, is where the temperature jumps from 15,000 degrees to 1.5 million degrees. So it shifts in transparency because now it's the X-ray corona, and you'd have to use another telescope to see the rest. But this is already interesting enough as it is. This is the dynamics. Now you're seeing the material move up and down along the fields. You can see the field itself at times shifting, turning. That's what electrical currents do, large-scale electrical currents. They make the field shift around. And that's the scale that we're looking at. That's little blue box there is the field of view that this telescope was actually looking at. And this is a stunning achievement because you'll have to translate the currency for me here. But this is a penny at 10 miles. This is a half a franc at 15-kilometer distance scale. Imagine the quality of that telescope. And that's the small part above which sits the corona. Now I'm switching to this global thing, the observations in the extreme ultraviolet, where we combined 3 colors, 3 different wavelengths, to actually give you an idea of the thermal structure and dynamics of the corona. So red, green, blue are 1, 1.5, and 2 million degrees. It's dynamic all over the place. There's no quiet time. It's accelerated. The sun rotates once a month, as seen once every 27 days, as seen from Earth. And it has regions of strong emission, where there are these strong active regions, fainter background, that's where the pepper and salt sits, and these big black areas. The black areas are the coronal holes, where the field is so weak that the gas pressure, the dynamics in the gas, actually manage to blow the field open. That's where it reaches out into interplanetary space and eventually can reach Earth. Some of these things going on here are explosive. I'm going to show you a few more in some more detail. They can be really pretty. And you know by now what the scale is of these events. Another challenge, apart from the dynamo, is trying to understand why magnetic fields in the sun go unstable. Can we predict when they go unstable? Can we understand how, in such an explosion, that region decides to partition its released energy from magnetic energy into light, into energetic particles, hydrogen and helium ions flying at near light speed into interplanetary space, and this bulk kinetic motion of a big coronal mass ejection coming out. Well, in order to do that, you have to understand the magnetic field. In the old days, this is a long time ago, it doesn't say when, this is 10 years, it's a long time ago. We used to say we can make potential field extrapolations based on the magnetic fields we measure at the surface, and we can just do a comparison, a qualitative comparison, with the emission from the active regions. And sometimes you'd see that the emissions, it doesn't show too well on this screen in particular, but like here it shows reasonably well, that the alignments are good. And in some cases, like on the right-hand side, you can see that the alignments are really terrible. They're 90 degrees off. The regions on the right are the interesting ones that are going to flare more frequently, that are going to flare more energetically. So qualitatively, we figured it's the non-potentiality. Well, that's not a surprise. That's the energy that we need to tap. Actually quantifying how much there is and where it sits is harder. This is an experiment that goes back also about 10 years. That was the first step towards saying we can do this better. We can use something that carries currents in it. And we can make the comparison between before and the before and after difference is a big red blob. The big red blob is where that particular model said that's where the electrical currents are particularly strong. That's where the source of the energy of the eruption sits. And fortunately, at the time that this particular region erupted, the eruption was centered on that region. It had about the right energy. So why don't we do this all the time? Well, it was really difficult. In fact, this was one of the times we had an international team here at ISSI working on this, and it took us 1.5 years just to do that. Because we did it with 8, 9 different models, different codes, different approximations, different people working on the same data set. And they didn't all agree. I'm showing you the best match. Other models came out miserably. Some of them predicted less energy than the potential field. We're still trying to figure that one out because it shouldn't be able to do that. So we said, we'll do it again. We had a second team here a few years later working on a completely different data set. Many of the same players, same models. Was again a really good approximation with observations, except it was a different model. Now, we know why that is. We don't know how to fix it. The reason, there are 2 reasons. One is, in order to make an extrapolation of a magnetic field in a box, you need to know the sides of the box. We only know the bottom. We don't know, because we can't observe the magnetic field in the corona, the sides and the top. So we don't know what leaves a box. And we can't make the box big enough that it covers the sun. The computers don't allow us to do that. The second and probably more important one is the bottom itself. We can measure the component of the magnetic field that's pointing right at the instrument or away from the instrument. We have great difficulty in measuring the transverse component, so the inclination of the field away from vertical. And even if we can measure it, there's an intrinsic physical issue in that we can maybe measure the tangent, the general direction of the rod of the magnetic field, but we can't attach an arrow to it. So we don't know whether it's pointing towards us or away from us. We can do it in the towards and away from us, but not in the transverse direction. So we're always left with, well, maybe it's pointing this way, or maybe it's pointing that way. And that makes it really hard to do this. Maybe we could do stereoscopy. Maybe we can get measurements in multiple layers in the atmosphere to resolve that. Those are techniques for the future that we're dreaming about. In the meantime, our computers are getting ever better. And I guess if I had shown you this without the labels of model and observation, you could go, oh, there's two sunspots. Because in many ways, our models are getting really good at this kind of representation of reality. So we're hoping that in a statistical sense, soon our models will tell us something about why regions form the way they do and why they can explode when they do. The difficult part is, as always, what happens below the surface. Because I'm not going to tell you too much about these diagrams. They're meant to show you that there are a lot of efforts going on about modeling the magnetic field inside the sun, not for the full sphere, but in some details, either when they're emerging through the flow that shreds these tubes, or whether they're undulating and following a particular structure as it moves around. The problem is we can't say this looks reasonable because we have no comparison. We can't see what happens on the interior. All we can see is what happens when any such structure breaches the surface, at which point it becomes accessible to us. And even then it's really hard. This is an attempt to have one of these entangled, shredded fields come through the surface. And what you don't see, but what the sun definitely knows about, is that if there is an undulation on such a structure and it comes up, suddenly there's all that heavy material in a dip, and you have to get rid of that. You can't just suck it out. It can't flow off the magnetic field. You have to find ways for the magnetic field to reconfigure itself so that it can actually drop the heavy stuff and explode into space. All of those things are being investigated, and I would say in every one of them, people are making remarkable headway, but it's a challenge. One of the nicest, most recent things I've seen is this. This is almost an extension of the model that I showed you earlier with that region coming up through the surface, except now you're looking at it from the side and you're looking only at the atmosphere. This is where that internal structure was. This is where all the bubbling happened. And they made it into a movie that is not playing. Since this is an important one, I do want it to play. So I'm going to disconnect for a moment and see what happens. Sometimes it helps. There. The magic of restarting. They are using the same colors, the red, green, and blue for the 1, 1.5, and 2 million degrees that I showed you earlier. And what they're showing is that they can actually create a structure that is erupting and exploding, and then the materials are flowing around as we see it on the real sun. So there is now a pathway to doing this. It's still in a limited box. You can see the box being hit at the top by material trying to get out. And it's a repeating box. So whatever leaves on that side actually comes back on this side. But it's getting there. All we have to do is wait for Moore's law. We have to wait for the computational capabilities to double and double and double, and then we'll be able to do this properly. In the meantime, there are all these diagrams that we're still making, comparisons with observations. We have wonderful rendering software so we can try to think in terms of 3D magnetic fields that are evolving. And speaking of 3D, I'm going to switch back to observations here. There was a time when we could see the sun from 3 perspectives. This is at a time when we literally had them 120 degrees apart. So we see front and 2 sides that are actually the back. And I've cut it here so you're just seeing the side. There's this big explosion, the biggest one we've seen in terms of how the dark material is being thrown up. The dark material is essentially cool. It's 20,000 Kelvin. So it absorbs the extreme ultraviolet light from its surroundings. And this particular mass ejection is not a coronal mass ejection. A little bit did make it out, but most of it, as you see, is actually falling back to the surface. And it's executing what looks like a bombing raid on the solar lower atmosphere. If you look at what comes down here, that material falling down heats up the surroundings. This is cute. The extent of this explosion didn't dawn on us until we started rendering it in a different way. And I'm going to show it to you in a different way. We can look at the corona in these different colors. This thing that I've shown you, and there was that eruption explosion over there. And you think, well, that's a big explosion, must be a big coronal mass ejection. And then we said, what if we only showed you the differences, where things change? So we take out everything that is constant and show only the difference. Now, that's the one on the right. Look at how far that explosion reaches. It reaches across half of the sun. And that made a lot of sense in terms of other observations that we were getting, like this one. Here's the filament erupting. Look at what happens here. That region is connected over something like 500 to 700,000 kilometers away and rips apart the region that sits at the limb just because of the magnetic connections. And we've seen more and more of these events. So we're beginning to realize now that, yes, it's a challenge to understand why the active region of the sun destabilizes. There's energy there. Why does it go unstable? Until a few years ago, and we saw this, we had the means to see the whole sun evolving all the time, the front side, the Earth-facing side of the sun. We would assume that the perturbation had to sit in the region itself, something that came up, something that was moved. Now we know that at least another scenario is that something hits it from the side. Take a vial of nitroglycerin and put it on a candle in a storm. Something will trigger it. But it could be the candle or the storm or both. You have to think a little wider now than internal stability only. Now, back to the bigger picture. All of this flows out. Much of the corona is flowing away in the solar wind and stretches the field in this beautifully simplistic rendition Okay, people have learned to do better than these simple renditions of it. In fact, they could make renditions like this. So now you're looking at a simulated eclipse. You're not seeing the center disk, you're just seeing the structures. What you're looking at is a still rotating. So the field isn't moving. They've relaxed the field and said, let's freeze it and now rotate it and look at it from different perspectives. So you can see the complexity of interpreting something through a perfectly transparent medium. If we freeze this at the time of the eclipse of 2017, as seen from very near to where I live, I was looking at it from a few dozen miles away from there, and compared to the observation, to the models there, or in different renderings in the lower diagrams, the match is really, really good. And they've done this before. So in times, I have to keep stressing this, we're getting pretty good to model the solar corona as a foundation of the solar wind and anything that happens in the heliosphere in times of quiescence. We're still tackling the part of eruptions and explosions. Now, these explosions do something. There are too many words on the next slide. Just listen to me rather than try to read them. These explosions, the coronal mass ejections, when they interact with the Earth's magnetic field, do things that can actually cost us money. Energetic particles may even damage spacecraft or affect the health of astronauts. I'm taking it down to the surface of the Earth. When a large magnetic field hits another large magnetic field and starts things moving around, you induce voltages and currents. Currents in the ionosphere that couple to currents in the Earth's structure, or anything we happen to be building on the Earth that is conductive, like the power grid. And we've been doing a number of studies now in trying to figure out, not only in the detailed case, does a large geomagnetic storm actually bring down some part of the electric power grid because it does something bad to the high voltage transformers? Yes, there are cases of that. We've also done it in a statistical sense and said, let's do this controlled retroactive exposure. We know when the storms are, we know when the storms aren't. We can compare the grid in some state and the grid in another state. The result was that probably something like 5% of all of the serious problems that are going on in the electric power grid are attributable to the presence of strong geomagnetic activity. And I'm being very careful in how I phrase it. It doesn't mean that it actually trips it. It means that the power grid is extra stressed by the presence of geomagnetic activity, or because there's geomagnetic activity, some load change on the power grid causes it to have a problem. And a problem means a serious brownout, a voltage drop, a frequency shift that triggers all sorts of resets on electrical equipment, or literally a power outage. And it would cost us something like, in the United States, $5 to $10 billion a year. Overall, although it sounds like a big number, that's not a big influence on the economy, which is good. But it's more than we spend on trying to understand the phenomenon, which is also good. So if we were better at it, we could save ourselves a lot of money. People focus on worst case scenarios just because we're people. So we're like, what's the century level event going to do? Well, estimates for that are, this is going to cost us $1 trillion. Guess what? If you multiply $10 billion a year with 100, you get to the same number. And this, I think, is also a really nice realization, because it means that by looking at the moderate to severe cases that don't bring us down altogether, we can learn something useful about the extreme events without having to wait for the extreme event to hit us. Which brings me to the last bit, second to last bit of my presentation. What about the worst bit? If it hasn't hit us yet, how do we find out that it can happen? Well, there was another, I mentioned I had been here quite a number of times, another international team that we did on trying to figure out what the worst case scenarios were of solar magnetic activity, geomagnetic activity, radiation storms, etc. And we found, of course, that there are records on Earth. Namely, we can look in ice cores and in rocks for radioactivity, radionuclides generated by energetic particles coming down from the settings of the sun and interacting with things on Earth. What we did in that ISSI team was, for one, talking to colleagues at the University of Bern who had records of ice cores and basically saying, well, that chemical pathway you thought about isn't working. So we threw that out of the window. We were left with literally the radionuclides, which means carbon 14 to 12 ratios, beryllium 10. If you're more adventurous, there are a few others, chlorine 37, one of them. And we can find records in tree rings of bad things, really the extreme solar flares going off and particle storms happening every few hundred years. And now that we know, people are looking back further and further at higher and higher resolution, trying to find the oldest possible tree trunks they can. We can go back about 4,000 years in these records. 4,000 years with an event that happens once every few hundred years still doesn't tell you a great deal about statistics. We'd like to get more statistics. Well, how about looking at 150,000 stars, 100,000 of which are like the sun for a couple of years in a row? That gives you statistics. This is beginning to get me to the planets, exoplanets. But the Kepler satellites stared at about 100,000 sun-like stars for a few years. You get a few 100,000 years of statistics. And if you look at the stars long enough, which it did, for example, you can see them rotate. You can see, because their spots are unevenly distributed, the brightness gradually going up and down, as on the top hand of the diagram. And you'll see occasionally there are these tiny spikes, like the one on the right that just moves off that line. That's a major flare going off. The lower curve shows you that blown up to the best of the temporal resolution that the satellite was offering. And when we translate that, okay, I have to give you the scale. The biggest solar flare is something we call an X10, an X-ray brightness. But if you translate this particular event, it would be an X110,000. That's a big flare. How often does that happen? Well, again, that's one we're puzzling about. This is a diagram where we're basically saying, let's put together how many events of what energy happened. And it goes from the very smallest we can observe, which are incredibly frequent, with billions a year happening, to the lowest frequency ones at the bottom end, where that gray zone begins, where we see them once every 10, 20, 30 years on the sun. We don't have more records. We've only got 40 years of records on the sun. And this is intriguing. The sun hasn't shown us anything above that dashed line. But the Kepler data have shown us two stars that go here, right on the extension of the solar projection. So now we're really puzzling, still actually literally puzzling over writing a paper that says, how do we connect these dots? We have no records of energetic particles in thousands of years of radionuclide measurements, and we have a few stars that have this explosion going on. And by all means, those stars look like ordinary stars, sun-like stars, the right rotation period, the right spectral type. They're not double stars. There's no line of sight confusion. People point 8 to 10 meter telescopes at these things to try and figure out what's wrong with these stars or what's wrong with the sun. I can't give you the answer. Somewhere in that gray zone is where we sit. If we sit at the low end, we don't have to worry too much with our power grids. If we sit at the high end, we should make a power grid that can withstand something like that. Be nice to have an answer there. Anyway, yes, we are making headway by building telescopes, by using artificial intelligence, by using computers. I want to make one more excursion. If we move away from the planets to the furthest stars, we're getting to the domain of the exoplanets. Why are we interested in exoplanets? Well, we as a culture are interested in them because we're looking for life elsewhere in the universe, or at least trying to understand the habitability of other planets. So we're trying to get to understanding what the atmospheres are, for example, on planets that aren't terribly different from the ones that we have in our solar system. Well, we have a few thousand floating occulting disks now. Each of these occulting disks, exoplanets, has a little atmosphere around it. And I would say we should be combining that information, because both we as solar physicists and the exoplanetary people are going to be interested in the results. We, for example, because of this. This is a star where, with the best available means of analyzing spectral lines, Doppler shifts, Zeeman Doppler imaging, we've established that there's a big spot over the pole of that star. The sun has never managed to do that. So there have been questions, is that real? Or is it an artifact of our analysis method? This particular star has an exoplanet transiting, and there's the exoplanet transit path. As the star rotated, so on a later transit, the transit actually came across the edge of that spot. And this is really neat because now we're seeing that there is an actual intensity structure underneath the trajectory of that star, not an artifact of methods. There is a star spot that sits over the poles. This is a really odd combination. It's a very rapidly spinning young star with a highly inclined orbit of a planet. Most of the planets would, like they do in our system, go more or less across the equator. But you get the concept. With exoplanets transiting stars, we can get resolution of structures, dark, as in star spots, and bright, as in the faculae that surround these star spots, at a resolution that we would never be able to get from looking at spectral lines of the disk integrated brightness of the star as a whole. So there's a lot of promise here. Going back to the habitability issue is now put an exoplanet in front of a star and try to figure out what the atmosphere is like. Now, I'm giving you here an example of pretty much the worst case you can almost think about. This is Venus in front of the sun. If you missed it, you'll have to wait another 100 years for it because it won't happen again. But we did catch that one, and it's a really pretty picture. It shows you that the transparent part of the atmosphere here is very thin. The whole atmosphere of Venus is pretty thin compared to the size of the planet. So these are not the ones to go for. But if you want to understand planetary atmospheres by transit spectroscopy, you need to realize that the light you're looking at comes from this ring where the light has gone through the atmosphere. Hopefully you can start with a thicker atmosphere and bigger planet. But the light that's coming through the atmosphere is not the average light of the star. It's the light from the structure right behind that atmosphere. So if there's structure on the star, and we know there is structure on stars because the sun is a great example, you ought to know about the structure behind it. It's basically arguing for what ought to be obvious. You need to understand these two things at the same time. If you want to understand exoplanetary atmospheres from transit spectroscopy, you'd better know what sits behind it. And for me, as a stellar astrophysicist, I'm like, well, I'd love to know what's behind it because we really have a poor understanding of dynamos. People were really adventurous in doing this, but only very recently. This is a paper I picked up when it wasn't even published. It was in the archive phase, preprint phase, where people said, let's try to start doing this. And don't read the slide. It's mainly there for me to remember what I was going to say. Let's start with hot Jupiters, stars that are close to their star, that are big, have big atmospheres. And in fact, because they're so close, these are puffed up atmospheres, so there's more transparency to the upper layers. And see if we can, from the spectra, during the transits for these stars, find evidence for what structure sits behind them and what chemical structure, hazes, and even, yes, these people are very adventurous, wind speeds in the atmospheres of these exoplanets can be measured. And they found a mix that in some of the cases they found strong evidence for clouds and hazes in these exoplanetary atmospheres. And in some where that didn't show, they found strong evidence for signatures of the structures on the stars behind them. And I think this is a wonderful start for the future. The next generation of instruments, which will be hopefully in the class of the James Webb Space Telescope, the successor of the Hubble, large aperture telescopes looking at the infrared, where there's lots of molecular lines to look at, where we can begin to do that. So I'm going to round up here by saying, well, thank you for paying attention here, but also pointing out that it's not just an academic thing to want to look at the sun. This is a series of pictures taken at a time when the SOHO satellite, the European satellite, was still looking with all of its instruments at the sun, looking at the sun in the middle, and the chronographic images around it, sensitive to particles coming right through it. That's not snow, those are energetic particles shooting right through the telescope on their way to Earth. We live in the outer atmosphere of this star. We better understand it. Thank you very much.
Thanks a lot, Karel, for this beautiful talk. I'm sure there are some questions. Please.
Do we have any understanding what happened during the mountain movement? Did the dynamo stop, or did the magnetic field not come through the surface, or any other ideas?
The short answer is no. The slightly longer answer is twofold. The dynamo did not stop. There were sunspots at the time. They were they're nice records kept, for example, in the Paris Observatory. They were very infrequent, and they seem to be only occurring in the southern hemisphere. Why that is, we do not know. From the modeling perspective, we're getting more and more ideas about what might perturb them. And it seems that stochastic fluctuations in the way that regions come to the surface, in fact, influence how the next cycle, the strength of the next cycle. That it is the emerged field that becomes the seed of the next cycle. That emerged field comes up in a certain orientation, and it doesn't take terribly many odd organizations off the east-west line to upset the balance of field in the high latitude regions, in the polar regions of the sun, and that might lead to a strong fluctuation in the strength of the cycle and the strength of the dynamo. That's hand-waving. I was doing that intentionally. We have no dynamo model that can do this properly, but there are ideas.
Are there further questions? Yes, please.
You told us about the slow speeds of matter in the outer layers of the sun. Our giant planets have very high wind speeds, but are very cold. So this seems a bit odd. Why doesn't the sun have great speeds?
Define great speed. There's no large-scale organization in the large-scale speed. The smallest structures, the granular patterns that are the size of France, the size of Germany, Texas, and Brazil, have speeds that are typically of the order of a kilometer a second. So that's a good part of the sound speed, of order 5 kilometers a second. The next larger scale, that of the supergranulation, already falls down to a few hundred meters a second, and the very largest scales of the differential rotation, the meridional circulation, are of the order of a few tens of meters a second at the surface. I don't know the answer to it. There is, in the sun, nothing that organizes it on the scale of like what we see on Jupiter and Saturn. There are other stars where the pattern is inverse. There are other stars where the pattern is substantially stronger, but none of them in which we don't, sorry, I have to say that more carefully. We can't measure that meridional flow on any other star. We can measure only the differential rotation, or get an idea of the differential rotation, which is in part that shear. But nowhere does it get much stronger than 2 or 3 times the strength of the sun, as far as we can tell. So there's something that keeps the convection zone, probably in part the rigorous convection itself, I would say, if you weren't going to give me the counterexample, if there's convection in these giant planets also. So it's a matter of Reynolds stress transport, and I don't know the answer to it.
Further questions? Yes, please.
What do you think will be give you the biggest advantage towards understanding the dynamo model from the observations? Is it seeing the entire sun, even the poles, or is it getting more details with higher resolution?
I can see merits in both. The biggest challenge we have is understanding the budget of the flux between rising and submerging. We know flux submerges because we see the field and the sun disappear again on that time scale. We don't know at what latitudes. If we had the housekeeping budget of the sun's magnetic field at the surface, we'd have an easier time in identifying, validating certain dynamo models versus falsifying some others. So I'd say seeing most of the sun, ideally also the very highest latitudes, but at least a 2 pi structure, if not a 4 pi structure, would give us continuously over some years, would at least give us an idea of where flux goes. And it will give us information on flow patterns that are too weak now to pick out, but may still be important on an 11-year timescale. And if they also did seismology, do multi-point seismology, if this is the sun and I'm looking at it, all I can see are the waves that are either global or the ones that hop short distances. What we'd really like to have is the wave path that goes about 120 degrees out, because that's the one that touches the bottom of the convective envelope, which is where we think the dynamo, primary dynamo, is seated. So if we had 3 points of view with magnetographs and seismographs, I think we'd be really happy. Whether that's the breakthrough, I can't predict. This is, after all, science.
Yes, Sanushka.
Is there already kind of common opinion on what is dominating and heating the corona?
There are many dominant opinions about.
Is flaring dominating on small scales, or is it wave mechanisms dominating, or a good combination of both?
If I'm not giving you entirely my personal opinion on it, I'd say it's primarily driven by convective motions that set up stresses in the atmospheric field, inducing currents that are then dissipated. If you're asking about what the dissipation process is, that's a tricky one. And it's probably not separable, because once currents start to go and be dissipated and unstable on small scales, they trigger all sorts of waves. So then you might be arguing really about what's the pathway. If you're asking about the source, I think the preponderance of evidence currently is for magnetic fields that are stressed and tangled, the way that Parker initially formulated it for the corona. In the chromosphere, the answer may be different. In the chromosphere, waves and wave-like phenomena and associated flows, even differential flows between the neutral and ionized populations, are coming to the fore now that our computers can tackle this better and observations are getting better. The answer is much less clear for the lower temperature of the chromosphere.
Yes, please.
Yeah. What methods do you use to determine the magnetic field parameters at a specific depth of, say, a subsurface layer?
To measure it?
Yeah.
We can't. All we can measure is that there's a perturbation in the propagation speed of the waves that we're looking at the surface. As they come through the magnetic field, in part they scatter, in part they're absorbed, but primarily it's a change in propagation speed and an associated change in direction. They're basically being scattered about.
Polarizations or effects like this.
All we get is pressure modes, and pressure modes don't carry that information. No.
Yes, please.
You have shown us simulations inside the cube, and that uncertainty can come from the outside surface, and so you repeat it and complete it to a torus. But the torus has a totally different topology compared to the sphere. So what can you learn if the topology changes so dramatically?
I didn't do it, I showed it. There's a difference. All I can say is that our computers are not capable in doing so much of the solar atmosphere that it is necessary to include the curvature. We just can't cover enough with sufficient resolution to do that. But the point is probably not too far in the future that we really have to acknowledge that it is a curved structure. But at that point, I would say that we're also having to acknowledge that all these other regions that we're looking at are also evolving. So there's a lot of crosstalk. And we should really expand it towards something that is substantially bigger than the active region that we're looking at. I'm sure we'll get there, but not yet.
Yes, please.
What is
then causing that dramatic temperature change between a few thousand degrees and millions of degrees?
At the surface, you're basically looking at the glow of hot material that comes up from the interior. It's just radiating essentially black body because it's hot, it radiates. At the higher layers, you have to come up with something else. And something else I was answering earlier is a combination of waves. There's a lot of noise because of the convective motions in the sun, which also triggers these nice sound waves that we use to probe the interior. These waves couple to the magnetic field, either internally causing pressure modes to run up or because they actually shake the magnetic field. And on top of that, we have these motions that are convective, overturning, so they're moving field around. They're literally braiding the field into some entangled state. Each one of these is capable, if dissipated, of heating to well above the surface temperature. The reason it suddenly shoots up to 1,000,000 degrees or thereabouts is not that there's anything particular about the corona that makes it that hot, apart from the fact that it can't radiate at lower temperatures. It radiates too efficiently at lower temperatures, and it can't radiate at high temperatures because once you heat it to a point that the bulk of the material loses its electrons, you ionize hydrogen and helium, radiation becomes very efficient. So if you're still heating it at that point, the temperature will just shoot up. So once you're above the temperature where hydrogen and helium are largely neutral, which is the chromosphere, you suddenly shift to another radiative transfer mode that it has to go to really hot before it's no longer the line radiation, but largely the continuum radiation and some noise coming out in iron lines like the ones I was showing you pictures of. That's a somewhat confused answer. I can do better if I had a little more time, but the difference is mainly in how it can lose energy rather than that it's fundamentally different in what's being put in. I didn't quite answer the question, but okay. We'll try again over. There's a combination of, the material at 20,000 degrees has a very strong stratification still to it. So the density is dropping very rapidly. And if on top of that, you put that loss of the structure that can radiate, apparently, you can make apparently, that's what it does, make a very rapid transition to higher temperatures. Very rapid is still a few hundred kilometers. It's not instantaneous. But at the resolution of these images, it looks like it just jumps. This is why it's called the transition region. It does something magical. Very few people dare touch the transition region.
Are there further questions? Yes, still one, please.
We observe 11-year cycles are comparable in other stars.
I should have mentioned that. Yes, the answer is yes. There are some observatories that have been looking at a few dozen stars for several decades without interruption. They have discovered cycles. And in that, it turns out the sun is somewhat atypical. The more active, the younger stars are all rather chaotic or flatlining, but at a high level. A star that is as old as the sun, it looks like sort of 1 in 3 has a cycle as pronounced as the sun, which means 2 in 3 do not. And as you narrow the sample, some of my colleagues in Boulder have been trying to do that, you of course have fewer elements in your sample. You get to like half a dozen. There's only one that shows a cycle, which is the one we live next to. So there's a puzzle. The sun doesn't have to be in this mode, although to the best of our evidence, as far as we can look back in all sorts of records on the Earth, it's been doing this as far as we can look back. That's a hard one to answer. The longest records are of order 30 years. Most of the cycles have periods that are between 3 and 15 years. The longer ones may have escaped notice so far because we've not been looking long enough without interruption. But there's a good deal of variety. No, they're not all of the same length.
Last one, please.
Climate change is a big issue now. Can you say anything about the solar effect on our planet?
One has to be very careful with answering that question because a lot is riding on it. The sun has varied considerably. It's varied tremendously in its output in extreme ultraviolet and X-rays, orders of magnitude going through cycles. The bulk bolometric irradiance changes by a fraction of a percent, 1/10 of a percent, thereabouts. And I don't think we have any reason to think it's ever been stronger. Our climate colleagues say that that might have been enough to cause the fluctuations in climate that we've seen from before 1900 for a few centuries before that. Not going into longer, because then you get into orbital perturbations and the tilt angle changes and the precession and nutation due to the moon pulling are going to get into the game. But the International Intergovernmental Panel on Climate Change says that the driver due to solar fluctuations is minute compared to the drivers that people are putting into the atmosphere. So it has driven climate. It definitely drives climate on a billion-year timescale because the sun is evolving. But if you're asking what does it do currently in the 20 to 50-year timescale, the answer seems to be it is not a player in that.
Okay. If there is not an urgent question right now, then I think one could continue also during the apéro, for which all of you are invited. And thanks a lot, Karel, for this wonderful talk. With this, I would like to close today's session and just briefly announce the last talk that we will have this year. It's a long break now until end of October, 30th of October, when we will go back to Earth, where Annika Snav will inform us about sea level measuring, sea level rise. With this, I hope you will enjoy the rest of the evening. Thanks a lot to Karel and for you to coming and enjoy the apéro. Thanks a lot.